All right, guys, welcome back. So this explain is going to be really long. It's going to be a really long explain. So it's going to be divided up into at least two videos. Okay, we're going to start with the first one, right? Because we really want to make sure that we're understanding osmoregulation, water balance, concentrations of salt and water in our blood. Now, our aim says, how does the body osmoregulate during exercise? Excuse me, let me drink some water of my own. Very refreshing. Now, number one says, which percentage would explain the net movement of water into a cell through the process of osmosis? Now, you have to recall, osmosis is the movement of water very specifically from an area of high concentration to an area of low concentration until equilibrium is reached, and it does not require any energy. We learned this literally during the osmosis onion cell investigation that we explored. All right. So any answer that would represent this has to demonstrate that water is moving from a higher percentage or a higher concentration to a lower one. And because we're talking about osmosis, we're only talking about the movement of water. I don't care about the movement of anything else except water. So I can cross out anything that does not mention water or mention something other than water, right? So A says water was 90% inside the cell and 95% outside the cell. Well, it does contain water. B says protein. I don't have to continue to read because I don't care about the movement of protein because it asks us about osmosis. And actually, let's before we answer this question, right? Let's just define osmosis. It's the movement of water from high. Actually, this is how I'm going to do it. It's the movement of water. That's what osmosis is. And these are three parts that you have to remember about osmosis. Water is always moving from high concentration to low concentration. That's always going to be true from an area of high to low, right? It requires no ATP energy. No ATP is used to move water. If that was the case, we would be in a lot of trouble, right? And it's going to keep moving until equilibrium is reached, all right? So let me just show you exactly what this might look like, okay? If this is a beaker and I have some type of membrane that divides the beaker, and these are my water molecules. 1, 2, 3, 4, 5, 6 water molecules, okay? Water is going to contain, I'm starting out at a high concentration on this side, which means that this side has to be a low concentration because there literally is no water on that side. But over time, let's say over maybe 15 minutes or so, in that beaker with the same membrane, I'm going to have 3 water molecules on each side because that is equilibrium, right? We have 3 on the high side, 3 on the low side, but now there is no high and low side because we have the same amount on both sides, right? So that's all that osmosis is really talking about. It is just the diffusion of water, the movement of water from high to low. No ATP is required, and it's going to continuously happen until equilibrium is reached. These 3 are going to head to that side. All right, we don't want all 6 water molecules to move to that side because then that's not equilibrium. 3 are gonna have to stay, 3 of them are gonna get pushed away. Ooh, that's a good rhyme. 3 are gonna stay, 3 get pushed away. All right, so now that we're equipped with that visual, let's answer number 1. So remembering that it's high to low. So if I look at A, I crossed out B because it contained protein and I don't care about the movement of protein. Letter A says water was 90% inside the cell and 95% outside of the cell. But the question is asking me water moving into the cell. So that means that naturally I have to have a higher percentage outside of the cell in order for water to naturally move into the cell. Is that what letter A is describing? It actually is. Water was 90% inside the cell and 95% outside of the cell. 95 is a higher percentage than 90, and 95% outside is higher than 90% inside, so water is going to naturally move into the cell. But let's take a look at letter C. Water was 95% inside the cell and 90% outside the cell. Well, if that's the case, then water would actually move outside because there's a higher concentration inside. But the question is asking me that water is going to move into the cell. So I can cross out C. And then D says water and protein. Don't care because it mentions the word protein, so I don't have to even keep reading. A is the best answer choice here. Now, number 2 says, base your answer to the following question on the information below. Select the laboratory procedure chosen from the list below that best applies to that statement. Each procedure uses a sample of peeled raw potato whose dimensions are 2 centimeters by 2 centimeters by 2 centimeters. The laboratory procedures are as follows. Number 1, place 2 drops of methylene blue solution onto the potato sample. 2, place 2 drops of iodine or Lugo solution onto the potato sample. 3, weigh the potato sample and place the sample in a beaker of distilled water for 30 minutes and then remove the sample from the beaker and reweigh. And then 4 says, weigh the potato sample, heat the sample for 5 hours in an oven at 80 degrees Celsius, and remove the sample from the oven and reweigh. This procedure demonstrates the effects of osmosis. So which one of these 3, 1, 2, 3, or 4, which one of these 4 represent osmosis? I'm going to choose any answer that talks about the movement of water only. Number 1 mentions methylene blue solution. Is that water? No, it is not water. Number 2 mentions iodine, Lugo solution. Is that water? No. Number 3 mentions distilled water. Is distilled water water? Yes. And then number 4 mentions heat. That's not water. So 3 is the correct answer here. All right, and let's just get some small notes. Distilled water, pure H2O, right? There's no solutes in that water. It's distilled. That means that it's 100% pure water. Okay? There are no solutes, there is no minerals, none of that stuff. It's 100% just pure pH level 7 water. That's what distilled water is. Now, part A, osmoregulation feedback chart. Directions say, with your group, outline an initial sequence chart that represents your thinking on how the human body carries out osmoregulation in response to exercise in the space below. Remember, use arrows to represent one event or stimulus to another from start to finish. You may want to do this in pencil. All right. So I left you guys a lot of space, and you're probably wondering why. Because we need to make a feedback chart on osmoregulation, right? Which is water and salt balance. Okay. Now, as a result of osmoregulation, remember, anytime that I do a feedback chart, I like to start at the top and then rotate clockwise, right? So I'm going to just start with hydration, right? Drinking water, which is hydrating ourselves, right? As a result of drinking water, what would I expect? Well, I would expect that water concentration in the blood increases. Just like how if we ate glucose, our glucose concentration in the blood would increase. If I drink water, water concentration in the blood will increase. But I don't want water concentration to necessarily increase without a nice balance. Okay? So, as a result, the kidneys will have to filter out water from blood and produce urine, right? So the kidneys are going to filter water out from the blood and help us to produce urine. We want to make sure that those blood cells don't overexpand or overinflate with water because then they risk popping and dying. And we don't want that. We need our blood. It does a lot of really great things for us, right? But let's say I'm exercising, then the sweat glands produce sweat, right? So my urine output is going to essentially decrease if I'm exercising because my sweat glands are producing all of that sweat for me, right? It's doing all of that regulation of salt and water for me. I'm going to get rid of my water through sweating, not through urination. It's very rare that you're going to feel the need to urinate after you just ran a marathon, right? We're going to rely mostly on sweat, right, as an immediate balance tool that we have for osmoregularity. Now, from there, that arrow was hideous. Okay, still hideous, but that's okay, right? From there, we have excretion, right? So the removal of wastes of urine and or sweat from the body, right? This is going to lead to what's known as dehydration, right? So when the kidneys are filtering out water from the blood to produce urine, that's going to make me go to the bathroom and release all of that urine, right? But because that urine output is so high, I risk the potential of getting dehydrated because there's so much water inside of my urine that I'm getting rid of, right? Same thing with sweat. If I sweat too much and I forget to drink water to replenish that, then I run the risk of dehydrating myself. So as a result, water concentration in blood decreases, leading me to drink water, right? And this is just really the normal balance, the negative feedback mechanism, just like blood glucose, just like thermoregulation, just like gas exchange. These are all negative feedback mechanisms, all to maintain balance. In this case, water and salt balance inside of our body, right? But it's also important for us to note that the nervous system and the brain is very present during all of these feedback mechanisms, right? It's the brain and the nervous system that's sending signals, that's releasing certain signals for us to increase our water intake. That's the feeling of feeling thirsty, right? We only feel thirsty because our brain is telling us you are thirsty and you need to increase your water intake. Now, once we've quenched that thirst and we've drank enough water, the brain is going to now send signals that says, okay, you can stop drinking water now, right? Because we don't want to overhydrate your cells or anything of that nature, all right? And we don't want to put too much pressure on your kidneys to have to get rid of all of that water all the time, all right? We want to make sure that we have a nice balance, right? So the nervous system is the one that's sending all these signals when we're hydrated, when we're dehydrated, to drink water, to stop drinking water. All of that is regulated by our brain. So we want to make sure that our brain is nice and intact because that's going to be super duper important for us. Okay? Now let's move on to part B. Osmoregulation at the system level. So let's read and annotate the important parts of the text. Humans lose about 2.5 liters of water per day through sweating, exhaling water vapor, and urination, right? So there's three different ways in which we lose water. Sweating, when we exhale water vapor, little droplets, and then urination, which we all do, right? And at 2.5 liters of water per day, that's a lot of water. No wonder why they recommend that we have at least 8 glasses of water per day, because if we're losing 2.5 liters of water, that's not great. That's not great. We have to have a way of replenishing that. Let's continue. This must be balanced with water input. That makes sense based off of what we just spoke about. Our tissues produce around 300 milliliters of water per day through metabolic processes. The remainder of water output must be balanced by drinking fluids and eating solid foods that contain water, right? So we definitely want to eat like melons, like watermelon, cantaloupe, honeydew melon. All of those are very high in water intake. That's just as good as part of those quote unquote 8 glasses of water that you're supposed to drink. The average fluid consumption per day is 1.5 liters, and water gained from solid foods approximate about 700 milliliters. So we only get about a little over 2 liters of water per day on average, even though we're losing about 2.5 liters. So at this point, we're losing more water than the average person is putting back into their system on a daily basis. So overall, that might lead to dehydration, right? Let's continue reading. So thirst is an osmoregulatory mechanism to increase water input, right? That's pretty simple. We become thirsty when we need to increase our water input, when we need to drink water. The thirst mechanism is activated in response to changes in water volume in the blood, but it is even more sensitive to changes in blood solute concentration. The urge to drink results from a complex interplay of hormones, the kidney, and the brain. That's what we literally just spoke about here. That is all regulated by our nervous system, our kidney, and the brain sending signals, or there's being hormones being released. Once the brain detects that there is not enough water or that there's too much solute in the blood, we feel thirsty, right? If our blood is very, very salty, that means that it's lacking a lot of water. That makes us feel very thirsty, right? And that's going to stimulate us to drink more fluid until we have a more normal amount of water in our blood. Okay? Now, if we look at number one, it says, how is the thirst sensation triggered in the body, right? So the brain detects, and again, this is all coming from the reading. The brain detects that there is not enough water or too much solutes in the blood and sends signals to stimulate thirst sensation, right? We feel thirsty because our brain is telling us you are thirsty. There's not enough water in your blood. You need to drink water now. Now, when does the thirst sensation stop? Well, the thirst sensation stops once, wait, that is really sloppy, my bad. The thirst sensation stops once we have consumed an adequate amount of water once we've consumed an adequate amount of water and water and solute concentrations in the blood are balanced, right? This is a good thing. And then this one is not a good thing. We don't want to be thirsty. We want just the right amount. Okay? Okay. All right. So, sorry, guys. All right. So let's continue to read. At the same time, our blood is moving through the kidney. The kidneys filter about 190 liters of blood and produce on average 1.5 liters of urine per day. Urine is mostly water, but also contains electrolytes and waste products such as urea. The amount of water filtered from the blood and excreted as urine is dependent on the amount of water in the body and the electrolyte or solute composition of the blood, right? So that goes hand in hand with the mini investigation that we did on water intake, right? The higher our water intake, the higher our urine output. The lower our water intake, the lower our urine output. Kidneys have protein sensors that detect blood volume from the pressure or stretch in the blood vessels of the kidneys. All right, so blood volume, the kidneys are able to tell just how much they need to filter by different pressure signals in our blood, right? And in our blood vessels. So let's look at number one. Blood volume in the kidney is low, leads to less water in the urine, more water retained in the body, and a decreased concentration of solute or sodium in the blood, which equals normal water and solute levels in the blood maintained, right? So when blood volume in the kidney is low, there's less water in our urine, which means that the body is trying to conserve as much water and retain as much water in the body as possible, right? But if we're trying to do that, then we're going to have to let go of more sodium or solutes from the blood, right? So that's going to lead to a low urine output, right? Low amounts of water in the urine, but higher amounts of salt and urea, which is what we just keep repeating over and over again. Now, the brain, the good almighty brain, also produces and releases antidiuretic hormone, which is ADH, which travels to the kidney to promote water reabsorption and conservation in the blood. This helps the body maintain water and solute balance in the blood when blood volume is low, right? So the brain is also going to come in with its own hormonal cocktail, if you will, is going to go to the kidney and it's going to tell the kidney, don't let go of all of that water into that urine. You go ahead and reabsorb some of that water back into the blood because we need it. This person cannot afford to lose any more water. So an antidiuretic hormone is going to tell the kidney, you need to conserve just a little bit more water than you are intending to. Now, number two says, blood volume in kidney is high. So when blood volume in kidney is high, less water is retained in the body. More water is let go in the urine. And there's a higher concentration of solute that's retained in the blood. And that's going to restore normal water and solute levels in the blood maintained, right? So when we drank so much water, our body is going to switch from trying to conserve water to now letting go of more water to now trying to conserve sodium and other solutes in the blood instead of trying to let go of those, right? Just to maintain water and salt balance. That's all this is talking about, okay? Now, number three says maintaining water balance in our blood is especially important during exercise. So 3A, an increased amount of exercise means more water and solutes released in sweat and urine, which is going to increase our thirst. That's pretty simple, right? And then 3B says a decreased exercise, or if we're at rest, that means less water and less solutes released in sweat and urine, decreased thirsts, right? If I'm not doing anything to let go of more water, like increasing the amount of exercise that I have or that I'm doing, I shouldn't feel the need to be so thirsty. Think about how you feel after gym. After gym, you're like, oh, can I get some water? Can I get some water? Can I get some water? It's very rare that you're gonna just be like kind of sleeping and you're just dying of thirst, right? Because your body is not exerting or releasing large amounts of water at all. Now, unless you get up in the middle of the night to urinate frequently, then yes, you are going to have to drink water before you try to fall asleep again to restore that water that you just lost. Okay? That's all this is saying. And by now, we should see that this is a feedback mechanism, a negative feedback mechanism. Now, in our cells, A, too much water and too little solute in the blood leads to water moves into cells, cells swell and can burst, right? So when we have too much water, if this is my cell, whoops, if this is my cell, right, and I have too much water, right, let's say I only have two little water molecules inside of here, right, and too much water goes into my cells, right, not maintaining a balance, that can lead to the cell literally expanding and expanding and expanding and expanding until it pops, right? We don't want that. We also don't want 2B, which is too little water and too much solute. Water is going to then move out of the cells and shrivel up, right? So if we have more water outside of the cells and water like literally leaves the cells, that means that cell is going to become a nothing burger. It's going to shrivel up. It's going to look really sad. It's like a deflated balloon. Therefore, therefore, during strenuous exercise, the nervous system, circulatory system, and excretory systems work together to maintain a balance between water and solute concentrations in the blood. All right? When we talk about strenuous exercise, think about the marathon runner. Yep, we're not over. Think about a marathon, right? When we think nervous system, we really want to think the brain. When we think circulatory system, we really want to think blood. When we think excretory system, we really want to think kidneys. Okay? And they're all working together to communicate with each other to say, hey, we need to maintain the amount of water and salt in the blood. Now, when exercising, it is important to stay hydrated. Some athletes consume sports drinks during exercise. Sports drinks can have a wide range of ingredients, including a lot of sugar, vitamins, and even caffeine. However, most sports drinks are primarily water with some dissolved solutes such as salt, sugar, and electrolytes. When sweating excessively, sports drinks may be helpful rather, as they replenish both water and the salts lost in sweats, right? So things like Gatorade and Powerade and things like that are really great choices after you've done a strenuous workout to replenish not only the amount of water in your blood, but also the amount of salts and electrolytes inside of your body as well. Now, part C, summary task. How does the body regulate water and salt balance, osmoregulate, right? So this is just asking you to describe osmoregulation, right? Water and salt balance. When this is too high, this happens. When this is too low, this happens. How do we regulate that? Not going to answer it for you. This is all you, a summary task. Number 2 says, why do we say that osmoregulation is a negative feedback mechanism, right? If you go back to the engage of thermoregulation, where we spoke about negative and positive feedback mechanisms, why is this osmoregulation, water and salt balance, considered a negative feedback mechanism, right? And not a positive one? And then number 3, how are water and salts regulated at the cell, organ, and body system level? Give one example of each, right? So at the cellular level, if I need to maintain water balance, let's say in a yeast cell or an amoeba, in bacteria, what are they going to use in order to do that? Well, it has to be something that's controlling the amount of water that enters and exits the cell. And the only organelle that controls the movement of molecules into and out of the cell is the cell membrane. Okay. At the organ level, right? What organ have we been talking about literally the last couple of lessons? That's going to create that urine for us and make sure that we regulate the amount of water in our blood as it's filtering our blood, are the kidneys. Okay. And the kidneys belong to which human body system level? You guessed it, the excretory system, right? We literally just annotated that here. The kidneys are part of the excretory system. Okay. And I'm going to let you elaborate on each one of these, but numbers 1 and 2, those are really important questions. And believe it or not, our explain to is actually not done, but this video for now is going to be done. Catch part 2 of our explain to right after this one. You guys are absolutely amazing, and I'll see you guys next time. Bye.